Yeah, yeah.
I can.
Yes, for me it's okay. I can see it very well.
So during the presentation, I'm going just to ask you to cut your microphone. Can you see the button to cut the microphone?
Okay, yes.
Okay.
Os dois trabalham na mesma equipe. Estão há muito tempo.
Obrigado.
Só confirma para ligar certinho, né? Para reforçar aí, tá?
Está funcionando. Beleza, obrigado. Valeu.
Professor, a bloqueio, o Thomas não entrou ainda, não sei se a gente espera mais um pouquinho ou se a gente...
No, I think we should go. It's 9, you know. Se ele entrar, a gente dá welcome. Okay, now our official good morning and good afternoon. I have the honor to declare in the name of the graduate officer of the School of Engineering, UNICAMP, officially open the thesis defense in a public session of Luiz Alfredo Pires Barbosa. The examining committee is composed by, at my right, Dr. Daniel Albiero from FEAGRE, UNICAMP, Brazil, Daniel. Dr. Vincent Richefaux, a researcher at the University of Grenoble and also at the laboratory 3SR, both in France. Dr. Jean-Yves Delaine, a researcher at the INRI, the French National Institute for Agricultural Research, and also at the University of Montpellier, both in France. And last but not least, Dr. Angel Pontin Garcia, to my left, who is also from the School of Engineering, Agricultural Engineering here at UNICAMP, and he actually holds a position as director of the school in his first year of a 4-year term, so he has a lot to go. Good luck, yeah? And I thank you all in advance for taking your time to participate in this section. I'm pretty sure that your experience and your expertise will enrich our discussions. I have a special thanks to Dr. Albiero, who was accepted to participate in such a short notice before the impossibility of Dr. Nunes. I also thank you for the audience, and that I hope they come to support Luis. And now, I'm very glad to introduce the candidate. Luiz Alfredo Pires Barbosa, a Brazilian, was born in Barra Bonita, São Paulo, completed his BS studies in agricultural engineering in 2009, completed his master's degree also in agricultural engineering in 2012, and started his PhD in August 2015. So his doctoral program is equivalent program to the PhD program in the USA. During his program in 2017, he got a scholarship from the Brazilian government, and spent 11 months at Agroscope, Switzerland, under the supervision of Dr. Thomas Keller. So now Luis will proceed with his presentation of approximately 30 minutes. Okay. So Luis, please.
Next week.
Luiz, só confirma se todos estão na sala, porque dá a impressão que um deles precisa de link para desconectar.
Vincent, can you see us?
Travou, hein? Conecta ele de novo.
Ele tentou entrar na sala de novo.
Just a second, Jay. It seems that Vincent has lost his connection.
Yeah, I see that, yeah.
Ele travou.
Então, mas ele tem que sair e entrar de novo na página.
E agora?
Okay. It's okay. It's coming back. So, c'est bon, Vincent?
Você não consegue mandar um e-mail para ele, Luiz?
Você consegue mandar mensagem?
Uma mensagem, um e-mail, uma coisa assim? Um chat? Ele tá na casa dele.
Não, ele está no office agora.
Ele tá no office?
É. Ele estava na casa dele.
Então, meu vídeo tem se finalizado.
Não,
Mas foram
O Luiz sim tem que avisar. Ah, mas os franceses estão sem terno.
não, fica tranquilo.
Eu sempre vou de terno.
Nós temos uma razão que me interessa, eu vou falar no final.
Voltou.
Good.
Voltou.
You're back.
Vincent, can you hear us?
Now we might.
Good.
Ele perdeu o que eu falei ou
Acho que interrompeu.
Je peux te voir,
Não sei que
il faut que tu fermes une des deux pages.
So I'm going to start my presentation now. Just a second to share my screen with you. During my presentation, you can stop me any moment that you have some problem to hear or to see the slides.
Okay.
Well, let's get started. Aggregate rupture governs a range of natural phenomena and technological processes. In agricultural soil, aggregates are responsible by controlling from environmental functioning to mechanical behavior. Breaking down soil structure may trigger environmental issues such as carbon depletion. Although a minimum soil fragmentation is required, our knowledge to design and obtain fragmentation by tillage is still unknown. Is still it requires more investigation. In order to improve this, to fill this gap, in this research, we focused on developing a numerical approach to model the rupture of soil aggregates in structure of bulk soil. This, besides improving our knowledge about the mechanisms involved in the fragmentation process, it also provide us better understanding to improve our prediction in terms of energy demand. Moreover, the parametrization method that take into account the hierarchical formation of the soil in the physical effect has to be established in terms to include in the parametrization method this scale effect on aggregate tensile strength. And also, since aggregate rupture is not always evident, we have to establish, to define a standard criterion to determine the force of the rupture. These three goals compose the backbone of this thesis, and each one resulted in a paper that I'm going to show you, to present you now in details, starting by the paper number 1, which evidence attests for soil aggregate rupture, a new criterion to determine aggregate tensile strength. The objectives here were to investigate the most appropriate criterion to determine the rupture force of soil aggregate, using the first force drop higher than 40%, a common criterion used by soil scientists, and the equatorial cracks formation, which is a criterion based on theoretical description. To do so, we have used the 4 aggregates. From the smallest to the largest, we have C1, C2, C3, and C4. To characterize the scale effect on aggregate structure, we have used X-ray microtomography across the cross-section of the aggregate in 3 regions: S1 near the top, S2 in the middle, and S3 in the bottom. Also, to characterize the effect of load on soil structure, we have used the aggregate from class 2 to also measure some features of the pore structure during the loading process in these 3 regions. Sound and visual evaluation were used during compression tests. This was to monitor the crack formation and propagation through the aggregate structure. And also, numerical modeling were used to verify and compare these both criterions. For the numerical model, we have used the software open source IAD, framework for discrete element model. And the aggregate were composed by spherical particles that were packed together using cohesive contact law, cohesive frictional contact law. And we have created models of aggregates with 4 aggregate sizes. Within the structure of the aggregate, we removed the particles randomly to mimic the porosity of the soil, and also to calibrate the aggregate density along the scale. And then, after the preparation of the models, we performed the simulations of compressive tests. As a result, X-ray data showed for the scale effect in terms of porosity, number of branches, and the number of junctions, which are mainly the length of the pores and the connectivity of the pores, respectively, a significant difference between S1 and S3 regions for the largest aggregate only. However, when analyzing crack size distribution, we see mainly two aggregate structures for all aggregate sizes. In S1, we have the smallest crack size distribution, while in S2 and S3, we have a larger crack size distribution. The load effect on aggregate structure can be seen in these plots, where we have a significant difference when we reach a load of 12 newtons. The number of branches for the S1 region significantly. However, although we have also trained to reduce porosity and branch length, it was not significant. An possible explanation about this behavior is that since S1 is closer to the contact surface, some pores near S1 region may collapse, reducing porosity and reducing the number of branches. This behavior can be seen during the compressive tests. In this example, we can see initial instant when the upper plate starts the displacement to perform the compressive tests. And then continuing with the displacement of the upper plate, we reach instant 2 when we have the formation of this surface deformation, and probably at this instant we have the collapse of the pores near the S1 region, reducing porosity and also branch length, number of branches in this region. And continuing with this displacement of the upper plate, we reach instant 3, where we can see the equatorial crack formation.
Você pode usar o mouse como computador.
These two instants are well identified in a characteristic diagram of force displacement synchronized with sound level. In instant 2, we have the first force drop higher than 40%, which has an equivalent of sound peak level. And also, continuing with the displacement, we reach instant 3, where we have a larger sound level peak. And also in this instant 3, we have the equatorial cracks formation. For more than 60% of the observations, the FED40 does not coincide with visible equatorial cracks. This was also observed in the numerical simulations, where in this example we show instant A, where we have the crack formation in the poles, and respective first force drop higher than 40%. Continuing with the displacement, we reach instant C, where we have the equatorial cracks formation, and in this instant we have the highest peak in the decrement rate of coordination number, the highest peak in the number of cracks, and correspondent rupture force. FED40 defines instant A as the aggregate rupture, and EC criterion defines instant C. Using these two rupture force, we calculate aggregate tensile strength and plot the viable distribution. So here we have the logarithmic scale of survival probability and against the tensile strength. From the viable distribution, we have mainly two parameters. The first one is the characteristic tensile strength, which is defined by the intersection between the dashed black line with the distribution. And also we have the slope of the distribution, which is the viable model. For all cases, increasing aggregate size, we have a reduction in aggregate characteristic tensile strength. But it's only for the AC criterion from simulations that we have closer values of characteristic tensile strengths and viable models to the lab measurements. In addition, we have used the correlation between viable models and crack size distribution obtained from X-ray tomography, and the correlation found for EC criterion was significant and higher than for the FD40. In conclusion, EC criterion seems to be a more appropriate criterion to be used hereafter. In this way, moving on to paper number 2, scale effect of aggregate rupture using the relationship between friability and fractal dimension to parameterize discrete element models. The objectives here were to evaluate if exists a relationship among friability, fractal dimension, and bond strength, and how it could be used to determine the model parameters in order to reproduce the scale effect of aggregate tensile strength. To do so, we have used the numerical simulations. In this case, we are showing the 4 sides of aggregate that we have used, and this scale effect of aggregate density is we can calculate fractal dimension. So we have used the different fractal dimensions and also the different particle bond strength values. For these different combinations, we have performed the compression simulations and measure aggregate tensile strength. Then 2 main relationships were get from here that are the relationship between aggregate tensile strength with friability and fractal dimension with friability. Laboratory measurements were also performed, where we have also different aggregate diameters and performed the compressive tests to measure aggregate tensile strength and calculate friability. Both numerical data and experimental data were combined to create a parameterization method, which is based on 5 steps. The first step is the use of the relationship between friability and aggregate tensile strength. The second step is using the experimental data to input in this relationship. The third step is a relationship between bond strength and the independent term in the first relationship. And this was used to calculate the bond strength. With the fourth step is the use of the friability and between friability and fractal dimension, which was fed by the friability value from the lab measurement to calculate the fractal dimension. Fractal dimension is important to calculate for the numerical model the density of the different aggregates. As a result, in this numerical data, we have in figure A and B the 2 main relationships used for the parameterization method. So in A, we have the relationship between friability and aggregate tensile strength for different bond strengths and also for different aggregate densities. The smallest aggregate has also smaller porosities. As we can see in figure D, we can see that for the smaller is the porosity, variations in bond strength represent larger variations in tensile strength when we compare with the larger porosity. For this, the use of smaller aggregates is more reliable to identify variations in tensile strength due to bond strength. In figure B, we have the relationship between friability and fractal number, and an important observation is that the rate in which friability diminishes with the increment in fractal number depends on the bond strength. Looking at the isolines in figure C, we can understand why. Each isoline has a black dot. This black dot is showing the instant when the slope goes from near 0 to a positive value. These black dots are happening in lower values of bond strength as the fractal number increases. This can be explained by as we increase the fractal number going to near 3, the effect of aggregate density does not affect friability in a larger way. Consequently, bond strength becomes more influential in the aggregate friability, in the soil friability. This brings concerns about the use of the practical use of friability for some soil scientists, as we discussed it in the paper. And then we use the aggregate tensile strength measured from the laboratory experiments and also plot the variable distribution. From this variable distribution, we have the characteristic tensile strength for each aggregate size represented by these different colors. And use this characteristic tensile strength to measure the friability of the soil. Merging these numerical data with laboratory measurements, we used the parametrization method to calculate bond strength and fractal dimension. With these two values, we run new simulations to measure the friability obtained from the model. As we can see here, the difference, the error between the experimental value and this parametrizated model was below 2%. In conclusion, a relationship among friability, fractal dimension, and bond strength was found. It enabled the creation of a parametrization method for discrete element model that successfully reproduces the scale effect of tensile strength on soil aggregates. And with this in mind, we move towards the paper number 3. Aggregate rupture on bulk soil, a model to quantify fragmentation properties and energy demand of tillage tools. The objective here were to apply the parametrization method to create a soil structure formed by a range of soil aggregates, quantify the level of fractal fragmentation per unit of energy required by two tillage tool principles, and use this numerical data to estimate fuel consumption. The tillage tools considered for this study were, first, a conventional furrow opener that we have empirical data about the draft force, for instance, which was important in the procedure for the calibration of the friction coefficient between the tool and the particles. And also, we have used a new concept of furrow opener that combines a furrow opener with a different geometry plus a rotary hole. The soil beam model with 1.2 meters wide, 2 meters length, and 0.5 meters depth was composed mainly by 3 layers. The top layer was composed by aggregates of 11 centimeters of diameter. The middle layer was composed by 12 centimeters aggregates, and the bottom layer was composed by 13 centimeters aggregates. In order to measure the fragmentation promoted by each tillage tool, we have to develop an algorithm to count the number of elements indicated by N and the size of these elements indicated by L. And this was important to calculate the fractal fragmentation number, which is indicated by dF. The algorithm identifies particles that are grouped together by cohesive contacts and forms an aggregate, counting the number of elements. In this case, it's starting with 2, for instance. When applying external force, some bonded particles may be broken, bonded contacts may be broken, and then the algorithm runs again and count the number of elements that we have. In this case, we have 3. It identifies 3. as results from the calibration procedure, we have used the friability of a chosen soil to estimate the tensile strength of the larger aggregate used in the numerical model. And as we can see, the friability obtained from the model compared to the friability of the chosen soil had an error below 4%. As we told, the draft force was used to calibrate the friction coefficient for the conventional tool. And here I'm going to show you just an example of this simulation. First, for the conventional tool operating at 2 meters per second, and then for the new tool concept, also operating at 2 meters per second with a rotational speed of 134 RPM. Then we compared the cross-sectional area of the furrow between the experiments and the numerical simulations for the FO2, that is the conventional furrow opener. As we can see in this purple and red area, similar geometries were obtained, while for the new tool concept that we are going to call RFO in green, we obtained a significantly smaller area as expected. The number of breaks is the particle bonded contact breakage. And in these plots, we can see the profile of the number of breaks promoted by each tool along soil beam depth, in this example, and along soil beam width in here. In addition to this, we have this color map highlighting the regions of each tillage tool that most promoted the particle breakage. These information may be important for tillage tool designs. Regarding soil fragmentation, this plot is showing the number of aggregates by the aggregate size. What is important to see here is the exponent of this equation, which shows the fractal fragmentation number for the initial value and for the value after the tool tillage operation. The difference between the final value and the initial value gives us the level of soil fragmentation promoted by each tillage. As we can see here, RFO has promoted 10% more soil fragmentation than FO. And here we have the draft force for both tillage. In the left, we have the draft force obtained from the numerical model for the conventional furrow opener, and on the right we have the draft force obtained for the new tool concept. In addition to this draft force, we have to consider the torque obtained required for the rotary hoe in this simulation to calculate the overall energy. Comparing the energy of both tillage tools, we found that the fragmentation, the energy used to promote fragmentation of soil was 5.6 times higher for RFO2. These energetic data were used together with the Canasoft platform, where we have the current scenario diesel consumption and estimated a fictitious scenario using the RFO2, where in the conditions of this study, the diesel consumption has a potential to reduce by 40%. In conclusion, the application of the parameterization method to model a soil being composed by a range of aggregate size enabled the quantification of soil structural fragmentation and energy demand of different theological principles. Therefore, as general conclusions, in this research, a more appropriate criterion was determined to obtain aggregate rupture force. A reliable parametrization method was established. And finally, an application of the method to build a bulk soil structure was successfully implemented. Thank you.
Thank you, Luis. Can we get the cameras back?
Yes.
Yeah, thank you, Luis, for your presentation. And as Luis takes a breath and position himself, I'll introduce the new step in this examination. That will be the examining and questioning part. Each examiner will have the opportunity to comment, to contribute, to question the candidate. And we understand that approximately 30 minutes will be a reasonable time, but we're not fixed to that. If you need more time, please feel free. I would like to invite then Dr. Daniel Oviedo for your comments and contribution, please.
I'd like to say that I like very much your papers, your thesis. I think that is a complex analysis, and in a fast time that I have to read, I have some constructive criticism. Okay, Luis. But every constructive criticism, if a question for you to talk with your advisor to decide what does this criticism you we was to use in this your test, okay? Luis, I like very much in page 9 that you put for us the hypothesis.
Okay.
I like very much is a very easy for us to analyze your results and your conclusions in function of your tests. I like very much this is procedure that you write. But it is my first criticism.
Okay.
You put clear for us the hypothesis, but in logics, you have ever to realize that hypothesis is a scientific method for two logics to result a conclusion. Okay, if a logic statement, if hypothesis, then thesis. Okay, and you put for us clear your hypothesis. If your hypothesis in the direct tensile straight test, okay, but you have working very much good work to prove your hypothesis with your results, but in conclusion about your papers, you don't prove or not prove your hypothesis.
Okay.
This is a question you to rewrite your conclusion, because in my opinion, the conclusion, the item conclusion in each paper will be the answer for question that your hypothesis should do. Okay, então, so I would like to you in conclusions for it is you get to prove your hypothesis, but in conclusion
It's lacking some.
in to write these results. Okay.
Do you have a specific example?
I will.
Okay,
Well, this is a main criticism for your is a format of your academic thesis. Okay. one technical suggestion, Luis, in page 30 for first paper. You put our soil characteristics in São Paulo soil, clay, silt, sand, organic matter. Okay, you use characters that for me your soil. But why do you know put in your text USDA taxonomy soil classification or FAO W or B classification? In a question, you have easy situation because with is your data, you go to this table of FAO or USDA and to classification. Okay. In page 16, you write for us in item 2.3, laboratory compression text. You write that you use 30 aggregate samples, okay? For each size class, okay? Why? Why 30? Luis, in my opinion, it's necessary to you to put for us the experimental design. What replication, water samples, why 30? It's a methodology of last sample for normality, okay? Explain for us why 30. Now, I would like to say that I like very much you're using Weibull probability distribution. It's exactly distribution for your situation, for your samples. But this is a motive. Why motive? I know very much Weibull distribution because I work in Ceará state for 8 years with eolic energy. And in eolic energy, for we to evaluate the winds, the frequency of winds, spectrum of frequency of winds in Ceará for eolic energy, we use very much Weibull distribution, but there is a motive. Why motive? In winds, is a phenomenon where we have samples of data in undeterministic frequency. Why? Because you have the wind, the mass, hair mass in moving, but you don't have a deterministic frequency because you have a gust, you have a storm. This is data are a characteristic of your frequency in this data. Soil, aggregate soil, is a same situation. So I would like to explain this. There is very much literature about this explain why Weibull distribution is the use for winds and two for soil. I think that you put this is literature here, but Weibull distribution is very good. It's a proof for your results, very good. Okay.
Just an argument here. I didn't explain why I used the Weibull distribution. I just cited the reference.
Yeah.
But because in my point of view, Weibull distribution is already well known in soil mechanics, for instance, and explaining this would promote a larger paper, you know. So just to avoid explaining too much, because this is right the paper we submitted. So
yeah, but in academic thesis is possible. But in the paper, you only related. You don't cite these authors. But in thesis is possible. You explain this. Okay. But in paper, yeah. Page 20. Okay. In item 2.7, comparing the rupture force criteria.
Okay.
You write that you did X-ray, CT scanning. Okay, your statistic analysis was a two-way ANOVA. Okay. Luis, It's okay. Results is very great, but for you use this is a statistical method, ANOVA, you must to prove normal distribution data. So I suggest for you that you is necessary to you do a statistical test for normalized data. Why? Because ANOVA just is a useful method if you have a standard deviation is a explain your dispersion.
Okay.
If you don't have normalized data, standard deviation not to explain your dispersion. You understand? So you have to put a statistical test. It's a simple
Yes.
kurtosis,
Yes.
answer Darling, one, but you need to put in a statistical test for normalized data.
Okay.
Yeah. In paper, it's very beautiful. Is great. This is a method for you to show your results in figure 3.
Okay.
It's very good. I like very much. But in a thesis, you must to show for us detailed data. You can to put in appendix.
Yes.
But it's necessary to show a NOVA table completely, degree of freedom, some squares, some mean, statistical F, significance. Is not problem. In appendix you put this. This is very important. Okay. In every your treatment, in every your results. Okay. In appendix. Okay. I would like you in your discussion about this paper that in page 27. I like very much your results. Okay, I like very much, very good. Is a possibility very big, professor, to publishing a paper in a journal with high level impact factor.
I think it was submitted already.
Yeah, it's very good. But Luis, is a potential is a huge potential. There's this result for me. You don't to use this potential. I would like you did make more discussion. Example in here in page 27. You write. Comparing both criteria with the laboratory measure is very powerful, The absolute value of characteristic density about for the FD40 were underestimated by approximately 30%. In action, using the EC criterion, simulation display an error in approximately 8%. Luis, this is very much rich, but you don't write sufficiently. I think that you is necessary you enrich this discussion. Why is happening? Why your explication for this? I think that this will be better for you to show this incredible tool that is then discrete elements. Page 29, conclusions. I say, I already say, I think that you must, in conclusion, to
Bring back
to hypothesis. And okay, references in this paper. Luis, I in academic thesis, in a standard work, standard right, it's not necessary. But in journals, high-level impact journals, high-level impact factor journals, we need more state-of-art papers.
Okay.
In academic thesis, I think that is good. Okay, no problem. But for you to publish this paper, I think that you is better you enrich more papers in state of art.
Okay.
I did a little statistics about your reference. You have in this paper, in total, 34 papers, okay? The 34 papers, you have only 21% in state of art.
State of art,
Yeah.
you mean like 5 years?
Yeah.
Within 5 years?
Yeah. List of 5 years. And you have 44, I call these papers in fundamentals. Papers more than years old. Okay? So in here it's okay, it's good. In academic thesis, no problem. But in a paper for a journal, scientific journal, is necessary to put more study of art. Okay. Okay. Paper 2, I like very much. I like very much your insight into funding dimension fractal with this friability. I think that is a great idea. I like very much. And
His idea.
is a great idea, but I don't I think that you same situation about last paper is necessarily you did more enriching in your discussion. Why you have this idea? Why insights you have? You understand? So I did some suggestions for you enrich your discussion, okay? But one point very beautiful in your paper, I like very much figure 4. Your results show a incredible result that you don't explore. You know, I am studying very much cause complexity theory. I like very much. I suggest some ideas for you, and in this result, I see an incredible discussion for you. You say for us in your presentation this interconnection and friability and dimensional factor and these results, okay, in figure 4. Okay, realize a point. Your limit 2.9 in figure 4C. Why 2.9? Is next to 3. Why? Many discussions you in another positions you stop very much next of 3, number 3. Why? Because every your discussion, every your ideas, when you to approach of 3 number, you is approach of limit of cause. In cause theory, we have a coefficient, Lyapunov coefficient. Is a number. This coefficient have a very next proximity with the dimensional fractional dimensional. Is dimensional fractional with Lyapunov coefficient is very much next in a theory.
Can you repeat?
Lyapunov coefficient.
Okay, Lyapunov.
Com what y. Lyapunov and every research in cause in the complexity theory to show for us that in many natural phenomena, soil, storms, DNA, that when you to approach 3 number, you arrive a limit of the organization. Yeah. If you trespass the 3, you go a regime, a situation on the cause. Every cause, total cause is domain. Is completely uncontrolled. Your results, there is a very strong literature to prove in your results that you comprove this Lyapunov coefficient about 3.
Okay.
This is a very rich because many researchers studying was studying about soil fragmentation.
Okay.
But no one did this approximation that you have in your results.
Okay.
The Lipnoff coefficient 3, the fractal dimensional tree is a very rich discussion for you. Okay.
This actually I have this insight to use this graphic in figure 4, letter C, from the observation of a paper where the guy investigated the formation of planets. So, but there is a different condition from aggregate because while in soil, increasing aggregate size, it reduces the density. In planetary formation, increasing aggregate size, we have increment in density because of the shock of the particles in the planetesimal ring. So they worked with a different approach, but the idea, I don't know if it's right to think, but they were using a fractal number higher than 3 because they get inverted the correlation between density and aggregate size. I don't know if it's theoretically, I think it's not right thinking in something higher than 3, but that was the insight I get from that
because
work.
3 is a Lipnoff coefficient.
Yeah.
Dimensional fractal dimensional is a dependent of Lipnoff coefficient. If you have dimensional coefficient, fractal dimension, you get Lipnoff coefficient for the number. Is a equation. Okay. Okay, Luis. Same case of after paper. In reference, you have 30% of papers in your reference in state of art, but you have 54% in fundamentals.
Okay.
So I think that you could to put more papers in specifics paper between 10 at 5 years old.
There is some reference here that are necessary to be cited. Perhaps I have to manage it to increase this percentage of reference within 5 years. But some reference here are really necessary. And they are older than 10 years.
I understand. In last paper, I have a few observations. Only observation, I like very much your page 69. If you did the deduction about your energy power equation, and I know that this equation is a classic mechanical equation, but don't your equation. It's necessary to use citate some authors for this. It's not necessary to cite Newton, but it's necessary to cite Halliday, Beer, Johnson. Okay. Okay. Semi suggestion about another conclusion hypothesis. Papers okay. I like very much your general conclusions. Very good. In general conclusion, you answer your questions in hypothesis. But I need this is necessary in each paper to answer each hypothesis. Okay, Luis, I finished my discussion about your thesis. I like very much. Congratulations, Luis. Congratulations, Professor Antonio Carlos. Very good paper. Very good advisor for you. And I returned to work for session sharp.
Okay, all right. Professor Daniel, thank you very much for your contribution, your time. I know that you will take all those into consideration. Now, I'll invite Dr. Vincent Richefort for his participation. Please.
Thank you. Thanks a lot. I would like to thank Luis for his presentation. It was good. The sound was not good. The sound was difficult to understand, but I read the thesis, so it's okay. Few words. I saw some typos in the thesis, but there are few. It is generally well written. It's easy to read also, except the fact that you in the three papers you use the style, material method, result, discussion. Are you obliged to do that?
Actually, no. That was a choose between my advisor and I. We just used the same structure that we used for the publication and assembled the thesis organized by this structure. As you can see, some paper like the paper number 2, this paper doesn't have the number for each section. That is because the journal, the style of journal didn't require this. So we used exactly the same style in this thesis organization. But this is a first draft, so that was, in our opinion, it was okay. But we can argue and we can improve this organization if you have some suggestions.
No, it is good. I'm not familiar with this style. Actually, it makes my reading more difficult, but
Yeah.
it's good.
Yeah,
Okay.
yeah. Here we have this flexibility that we can choose between a more formal style or this journal style.
Okay. So my general feeling is that the work is very good, actually. But my job here today is to make some criticisms.
Okay.
So I will do, but feel free with me. I'm not here to say bad things. My feeling is good feeling.
Okay.
So maybe with my questions, we will improve the document and maybe also the papers. I would like to know if the papers. I understand that the papers have been submitted. Can you say more about the journals you chose?
Yes, of course. Paper number 1 we submitted to the soil and tillage research. Uh, this paper has already a first revision, and now we submitted it to another revision from the reviewers in that journal. The second paper was submitted to the International Journal of Analytical and Numerical Methods in Computational Geomechanics. I think it's something like that because the name is pretty
Nine.
large.
We call it nine.
Yeah, yeah, exactly.
Nine,
Yeah,
nine, okay.
yeah. And also, this paper is in the same situation. We got the answer from the reviewers and the first comment to make the revision, and then we corrected and send back to the journal, and now we are just waiting. The third paper requires the paper number 2 to be published, so that's why I didn't submit the paper number 3.
Okay. But okay. Uh, so there is something I regret, let's say, in the reading of your manuscript, that there is no consistency between each part.
Okay.
For instance, the coordination number is called CN in one part and Z in the other one.
Okay.
It's not a big issue, but just a comment. There is something that was missing for me in the first paper. I was always needing some pictures. For instance, when you use the PG to process your pictures, your scans,
Yeah.
uh, uh, I cannot figure out what you call I don't remember the name. A junction and branch.
Ah, okay.
It's not clear for me to understand. So we need this kind of picture to understand what you are talking about.
Are you familiar with image analysis in ImageJ?
Yes.
Okay. Basically, we have the after segmentation of the image, we have the pores and cracks. Let's call everything that we have the flaw is called the pore in the image. What BoneJ is doing is like identifying the volume of the pore and promoting the erosion symmetrically of this pore till it finds the medial line of the pore, and then we call branch this medial line of the pore. And for all processing data, we use this name branch, that is the medial line, and then we measure like the length of this branch. We measure the connectivity between pores by the connectivity of this intersection of this branches line. Can you see?
In 3D?
In 3D, exactly.
Okay.
Yeah.
So this is the, okay. What you call branch is connectivity of pores.
Branch is the medial line of the pore, and junctions are the connectivity between these branches. Because when we have a cross formation, is like we have the contact of two lines of the branch, and then this point is called the junction, which is equivalent to the connectivity of the pore.
So this point is still very hard for me to understand. Okay, so a picture, a nice picture, a nice illustration would be a good idea.
Ah, okay.
Okay.
Yeah, perhaps I could use the figure used by the guys in the ImageJ. They have a really nice explanation about this branching and junctions. You know, perhaps I could use it.
Or maybe less 3D based explanation.
Yes.
Maybe more geometrical
Okay.
explanation would be, I think, better.
And for this explanation, you mean in the methods or in the results?
In the method,
Okay.
at the end, we've got some graphs showing the density of junctions and branches, and since I cannot figure out what they are, it's hard to understand. No, not that one. When you placed on the aggregates the S1, S2, S3, you did that only for one side of aggregates, one size of aggregates, or all the sizes?
We performed that division in 3 regions for all aggregate sizes.
So the position was not the same.
Exactly. We didn't get exactly the same coordination of the beam of the X-ray. That's true, because each aggregate size has a different position of S1 and S2 and S3. So the coordination of the beam in the machine for the X-ray was in different coordinations. That's true.
Okay.
We just performed the X-ray scanning, and then using this X-ray data in ImageJ, we selected in ImageJ what could be some region S1 and then S2 and then S3. It was more about feeling. The methodology to do that, it was okay. It is S1. It is closer to the top. In the middle we have S2, and in the bottom we have S3.
My question was because when I saw the figure 3, the one with box plots.
Yeah.
The first one with there's a lot of difference, for instance, for the porosity between the three samples of S1, for example. There's a
Yeah.
lot of difference. So I found this it was strange.
Actually, Vincent, this investigation was it was more exploratory, because if you think the number of experiments in running X-ray data is for soil really small, but with this we could understand that soil structure, while the scale effect of soil structure has some significance in terms of crack size distribution, which
I understand
yeah,
why. I understand why. It
which
was
which in my
curiosity.
opinion, is it could be or can be a potential feature to be explored in in future works.
Yes. Um, there was something in the two first papers when you explain the use of YAD.
Okay.
Yeah, I don't know how to pronounce the code for the you say you use that law to simulate bonds. You understand me?
I don't know what is that load.
That law, the force law. The force law you
Yes,
use.
yes. The
Okay.
contact law was the. Uh, it's
The one
difficult.
of Schultes, no?
Uh, JCF, JCF.
No, I cannot understand that way.
Yes, in INEAD, I don't know if in INEAD they have a reference to this standard, to a standard name for this contact law, but just a second, I can indicate to you the reference that I used here.
My point is that this is not a reference law. For anyone who read the paper, they don't know yet actually. This is not a force law, which is a standard one.
Okay.
So maybe I think also that you should explain that law.
Okay, I understand.
Because it is not standard, and we need this to understand things.
Yes, uh, I agree. I think, as I told to Daniel, since we use the same structure of the paper, so in the journal, I didn't want to extend to explaining something that was already published, and I just used here some reference like Donze 2012, and also Bruno Chiarelli from
Sure.
from
But
2015.
what I say is that okay for the reference, but you have to say some words, not a lot.
Yeah,
Some words
yeah.
to explain what this law do.
Yes,
Does.
for sure, for sure.
It, because the rupture may be due to energy criterion, to a force criterion, to a combined force criterion. We need to know that.
Yes.
But because I jumped to another question, because when I see, for instance, um, figure figure 6, that one, okay,
Figure 6, yeah,
that one,
yeah.
I see that for a long time between A and B, we've got a zero force.
Yes.
This is strange. It means that in between the two, the aggregate is not elastic.
They are elastic, but I think, in my opinion, what happened in here was like after the breakage of the contact points, perhaps since the particles are larger than the real soil, perhaps we lose this contact with the upper plate, because it promoted let's say a massive breakage of particles, and then aggregate decreases a little bit in size, and then the upper plate to get a bit tricky to get in touch with the aggregate. That is just a speculation. I'm not sure.
This is exactly the point. So we don't know what happened. And for me, for instance, Jean-Yves, that will talk after me, he made his PhD thesis on this kind of things, and his curve is not like yours. The curves of Jean-Yves are like the one of figure 5. So a more stiff rupture, let's say.
Okay.
So we are asking questions and we need this information. That's the point. Time over time. You said nothing about the velocity you use to perform the compression test, the simulations. I saw in paper 2 the velocity is 3 at the power minus 6 meters per second, and in the simulations there are 3 centimeters per second, which is fast.
Yes, yes.
It is 10,000 times faster.
Yes, that's true. In my parameterization method, I have to consider this difference of speed and integrate this to define the model parameters in order to reproduce the macro effect of aggregate rupture. But when using that, I can explain the use of faster compressive simulation is the computational time. When I used a similar compressive speed for the simulations, the computational time increased like exponentially. So even working with it more than 10 times higher, these simulations for 900 compressive tests took me like 2.5 months to be done. So
I know that perfectly.
yeah, I had to. So
I understand very well.
I just consider
is
that my parameterization method could be used also to work in a faster displacement ratio, and then it's a kind of optimization of computational time.
Okay. Also, when I see in the paper 3 the the movies you showed,
Yeah.
we see that the process is dynamic. Sorry.
Yes.
The triage is dynamic.
Yes.
So the rupture of an aggregate has to be dynamic also.
Yes.
So the question is fundamental. The rupture in the static state may be different of to the rupture in the dynamic situation. It is
Yes.
precisely the reason why the force law that you use in the dam, the way you break each bond has to be clearly explained.
Okay.
You can use a criterion which is based on the energy, for instance, which is based on something else than the forces. And maybe the results, your result fits very well. It works, clearly.
Yeah.
But I may ask the question why it works so nicely.
Okay.
Because your criterion is not a dynamic one.
Yes,
And it works.
you may my parameterization method is like for a quasi-static test, and then I extrapolate this quasi-static for a dynamic simulation. Is that your point, right?
Yeah.
Yes.
Yes. Well, I agree with you that perhaps it is a large step to explain something that is happening in between. Uh, but the contact law I have used is based on the cohesive bond strength, and we in this contact we have only the cohesive contact and the frictional coefficient, and there is no in this contact between particles there is no viscous damping. However, I considered viscous damping as global. I know that it can be tricky because sometimes it not reproduce the dynamic behavior. but I used a very small damping, viscous damping, just to adjust or to dissipate this kinetic energy, you know,
Yes.
because the
No,
contact
damping.
law didn't include this.
Also, you talk about the global viscous damping.
Yes,
What is that? This is
global.
specific to YAG?
Yeah, yeah. I don't know if it is some term for YAD only, but the idea of global viscous damping is like everything you have in your simulation scenario is within a viscous fluid. So the fluid is working like something to dissipate all the energy that is released from the system. So the overall, the global viscous damping is working like this viscous fluid. And my dynamic simulation is like a bulk soil is what was built in within this viscous fluid, and everything that happens inside this, in some level, get dissipated. You know, the movements and this
I
kinetic
understand, but
energy.
it is viscous. It is viscous because you can also use the contact damping, which is not. It is the same, but you've got an artificial force, which is not viscous.
Okay.
You didn't see it, no. So because the DM is dynamic by sense,
Yes.
but you wanted to make static simulation, so you have to control this. Sorry, I've got questions in the wrong order, but the fact that you've got 60 simulations in paper 1 and 60 simulations in paper 2 is due to hazard, or they are the same, or they are not the same?
The simulations that I have used in paper 1 are the same that I have used after the parameterization method in paper
Okay.
2.
Okay, it was just for curiosity. Here I've got a question about the coordination number.
Yeah.
You did not define it. The coordination number is not a standard thing. You have to define.
Okay.
Is it the coordination of bonds?
No, it's the number, the average of contact between particles. I mean, it counts the contact of each particle within the aggregate, and it makes like an average for each particle. You know, so in this aggregate we have an average of 5, or we have 3 contacts in average for each aggregate, for each particle. Sorry.
If a bond is in the tensile state,
The bond.
you may have the bond can be in the tensile state without contact. Yes or no?
If I understood correctly, the cohesive contact are predicting the tensile strength and also in shearing. So we can have the bonded contact breakage due to a normal tensile strength or a shearing process. And the value defined for shearing and the tensile strength were the same.
You can have a bond with a gap. This is my question. A gap and a bond at the same time.
I don't know if you understand, but I don't have a gap between particles.
In the normal direction.
Yes.
Only in the normal direction, your
Yes.
rupture criterion is a force.
In normal direction is like more Coulomb force, you know, where we have
I understand it's a kind of more Coulomb with a cutoff.
Yes, exactly.
So
Yes. When we cross the ipsilon axis, we go to a point that it ruptures and goes straight to 0. We don't have
bonds. It's possible to have bonds in the middle of the sample that are in tensile state and without contact.
No, it's not possible. That's not possible. I have only my cohesive contact only happens when I have a contact between particles. This law from Liad has an option that each particle has an area of effect. Every particle within that area of effect becomes bonded to this particle. But I set this area of effect to the same particle diameter. So I have only my contact, my cohesive contact is only when I have a physical contact between particles.
To create the contact, but the contact will evolve. It will evolve after.
I couldn't understand your question.
This journey to create, you say, if I've got a contact between two spheres, so I can set a bond here.
Yes.
But then, when you will load the aggregate, this bond will be able to open with a force, a cohesive force, and then separate.
Yes. When the tensile strength or when the shearing reaches the defined bond strength, and then we have a separation of the particles, and then it is no longer a cohesive contact. When we lose this cohesive contact is broken. If the particle touch again, it's only frictional.
Okay. So you need absolutely to explain the law.
Yes.
We need this to understand. I think that the definition of coalition number is not clear actually.
Okay.
Because we don't know what it is actually. A comment about the fact that no, not yet. About the Weibull distributions. They are nice. There's no problem with that. But the theory of the weakest link, that's it?
Yes.
It seems to me that this theory is not compatible with the fact that we've got the FG40 and the criterion. Because if we've got two criterion, it means that it's not the weakest link that provoke the rupture. You understand my point?
Yes. Let me gather my thoughts here. What is promoting what is mimicking the weakest link in this aggregate rupture is I think it's two parameters or two conditions. The first is that the rupture, the contact law, is mimicking some brittle rupture. So once the tensile strength is reached, the bonded contact is broken, and it is no longer possible to bond again. So that is the fact number one, that in my opinion is mimicking this brittle fracture. The second point is that the structure of the aggregate has some flaws, and these flaws, during the simulations, I could see the connectivity between the cracks. These flaws helps to the cracks to move from the poles of the aggregate, or even nucleation in the middle of the aggregate and within existing flow, and then moving to connect to the next flow, you know. So in this way, considering these two criteria, or these two parameters, the simulations could reproduce this question of weakest link of Weibull. I don't know if I answered you.
No, I was believing that the weakest link was the physical meaning was that you've got a weakest link who breaks, and this is the end.
No.
Okay.
So, but I see that the Weibull works perfectly.
Yes.
Nicely, because they are nice straight line. Often we see some flaws, but in the Weibull
I had just to complement your question. In NAG, I had a really nice question about a reviewer that asked me about this pore size distribution within the aggregate from the numerical model. And then to explain, I get the aggregates from the numerical model and create a lot of sections and use these sections in the same way I use the X-ray images in the image J, and then create this crack size distribution for the numerical model. And this crack size distribution has a similar effect on viable models that we see in this figure, because the smaller is the aggregate, the number of cracks becomes more heterogeneous, which means that the smaller the aggregate, the more heterogeneous is the tensile strength, which result in a smaller viable model. And increasing aggregate size, this crack size distribution become more homogeneous than the smallest aggregate. And then we obtained the higher viable models, meaning that the tensile strength is has less variability. So I think it works pretty well, and this question from the reviewer helped me to better understand my model, I think.
Okay. This is precisely that kind of things that are said by the Professor Nunes, that's it, that would improve your paper.
Okay.
Such analysis may improve a lot your paper.
Yes.
It's good. Your paper is good, but it needs some things like this. I will select my questions because I've got a lot, actually.
Take your time.
A comment, not in order. Between instant 2 and 3 in your test, that one?
Yeah.
You say that in instant 3 you see perfectly the equatorial cracks.
Yeah.
But when I look at picture of instant 2, I also see them.
Yes.
So there is a subtle difference that I didn't catch.
Yes. Actually,
Okay.
this is something that was already there, and instant 3 we have like a increase in this crack or this shade of this crack, and then I can see something. But this is after looking this picture like 100 times and seeing a lot of compressive tests.
Okay. But I understand it's hard to explain with a picture, actually. Just a stupid question. It is stupid, I think. But the criterion FD40, I think this criterion was there before you.
Yes.
So it looks like when I look at this plot,
Yeah.
that if the criterion was FD50, it would be the same that the equatorial crack.
I don't.
Did you try to? My question is: did you try to compare the EC with the FD50? Not 40, but 50.
No. Actually,
Maybe the same, no?
actually, I didn't know about the 50.
No, it doesn't exist. I just invented.
Yeah. The idea was use a common criterion used by soil scientists in this determination of tensile strength. Because during my experiments, I saw that if I use this criterion, something would be right. So I just tried to be as much as precise as I could, and in my opinion, EC equatorial cracks formation, as we can see in some publications like Rogovsky, showing that the crack formation in the equatorial region, we for sure have some aggregate failure. So that's why I went directly to the, in my opinion, most precise method and compare with the common used. And we can see clearly that the common used, we are interpreting the data in a wrong way sometimes.
Yes.
Yeah.
So if you can propose, I don't know, but if FG50 works,
Yes, I
we may
understand
say
you.
that
Yeah.
it is as easy to use as the FG40, but it is closer to the EC, to the equatorial crack protein.
Yes. Yes.
Maybe it's stupid. I know it's stupid.
Yeah. In this analysis, actually I did the observation of each aggregate compressive test. I think that's not in an operational way to implement in a larger aggregate analysis. You know, sometimes soil scientists are using different plots from different regions, so they have 100 of aggregates to be compressed. So they don't have time to look at the aggregate crack formation. But in my opinion, to be more precise, we have equipment that could be used like the sound and combine the universal test machine with this sound treatment. And then we can for sure have more precise data about the aggregate rupture. I don't know. And FD 70 may works. I don't know. We have to test because I told you that this is a characteristic diagram, but it can be really different for different aggregates because it can change with the shape. It can change with the moisture of these aggregates that it's not always in the same level. So the characteristic tensile diagram of force displacement can be really huge. In my opinion, the most precise way to implement in an operational way this evaluation would be with a combination of the tensile strength machine with sound analysis.
Okay.
In an automatic way.
It's less easy than using the curve force displacement.
Yeah, for sure, yeah.
Luis, I spent all my time to ask questions. I've got many other questions actually, but I don't want to spend all the time on that point.
Actually, if you have these questions written, send it to me and I can try to.
I can do that. I can do. I wanted to say that also that I would say one other time that the work is good. I feel really that the work is good. My questions was only to, let's say, to play the game. And you asked me a few times ago if I've got some opportunity for postdoc position.
Yes, I think we met
Yes.
in this conference.
Yes. For now, I don't, but I asked for funding for 2 postdocs.
Okay.
So keep in touch, let's say.
Okay.
All right.
Thank you.
Thank
you.
I will stop here
Great.
for the other.
Thank you very much, Vincent, for your participation and for your insight. Very interesting points. We shall be considering them, and we certainly will keep in touch. My suggestion now for a 5-minute break, so we can walk around and come back. Okay? I propose 5. If we're back sooner, we start sooner. Okay?
Okay.
Thank you.
Tudo bom. Se matar da alta. Valeu, obrigado.
Seu cara tá com a mão gelada, ó.
Não, tá bom.
Ah,
Eu tô suando. Eu tô suando.
Mas é, parece que tá friozinho. Então, cara, mas aquele negócio quando é sistema solar, tal, agregação é diferente totalmente do solo, porque o solo, a gente tem só uma força gravitacional, a gente é da terra, o solo tal. Quando você tem agregação, assim, de acreção, aí você tem o que? Variação no movimento angular.
Ok. Mas eu não lembro exatamente, mas eles não estavam tratando a questão o efeito de escala, sabe? Eles comentaram, ó, o efeito de escala de densidade é interessante para entender da onde veio esse corpo, qual estágio de formação ele estava no sistema. Né? Porque daí você consegue traçar, se você encontra uma relação entre densidade e tamanho, você consegue traçar em que momento ele foi formado.
Exatamente. E eu não falei, porque já tinha passado meu tempo, mas você também conseguiu no seu resultado, cara, mostrar que um variante. Você tem um invariante, cara. Isso ninguém publicou. No paper 2, você tem um invariante que a friabilidade.
No paper 2 inicialmente tinha 51 páginas. Eu falei do tanto, cara. Só que daí, tipo.
Mas você falou da invariante?
Não.
Porque você tem um invariante ali. A dimensão fractal mostrou que a friabilidade ela é invariante em função da escala. E a densidade não. Isso aí é forte, cara. Ninguém foi para esse lado. Ou seja, o que prova? A friabilidade é intrínseca ao solo. Ela é intrínseca. Naquela estrutura fractal de silt, argila e tal.
Preciso pensar um pouco
Esse
nisso.
negócio é legal, cara.
Porque a friabilidade, ela, às vezes os caras obtendo variação da força de ligação não obtinha variação da friabilidade. Mas essa é a questão, porque aumentando a coesão, você também aumenta o fractal.
Exato, exato. É um invariante, cara. É muito legal.
Vai estar apresentando. É que pra mim o tempo tá totalmente diferente.
Eu lembro disso, eu entendo. Muito sucesso aí.
Obrigado por estar aí. Vamos? Você me pode falar uma coisa pra trás, tem uma irmã aqui. Indo bem pra trás. São fáceis, né? Você trabalha na boa. Você não vai olhar no sol.
Quando vai ser a sua defesa?
Minha, ou de janeiro ou fevereiro. Quase terminando a tese de escrever.
A família já começou a apertar a sua
Já. Já. Eu vou entregar para ela essa semana. Pronto, assim. Só para corrigir.
E agora que eu vou
Mas vai acelerar?
Mas é que a gente aprende assim, né? Você precisa disso, né? Precisa subir o nível de subir e você conhece as comportas lá de barra, passadas por inteiro, não tem energia para subir o nível.
Que energia, viu?
Mas vale a pena.
Sim.
Isso faz sentido. Agora a gente trabalha mais. Depois você chega no nível depois você vai treinando as coisas que acrescentam no seu nível, você tem mais referência, né? Você já tem mais prática. Quando você está fazendo uma coisa nova, você está fazendo cada coisa nova, você está mudando a tendência de crítica. Isso é
Aí
Capes teses que eles têm, né, cara?
Tava olhando uma coisa aqui.
Pô, os caras arrebentam aqui na
Ô,
medicina.
Daniel, eu queria submeter o meu prêmio CAP semana que vem.
Cara, manda bala. Manda
Não sei nem
bala.
como
Os
faz.
seus, cara, tem que ver pra posar, mas acho que não é difícil não. É só você ter a autorização da CPG, né? Daí a CPG vai mandar pra Unicamp, a Unicamp manda, não é isso?
Não sei, cara.
Eu acho que não é CPF, eu acho que é institucional, né?
Pode ser.
Eu acho.
Porque quem ganha o prêmio, na verdade, é a
É
instituição.
instituição. Agora, na UFC era assim, cara. Aqui deve ser a mesma coisa. Você tem que conversar lá com a... FIAC só que não tem limite. Você pode mandar quanto quiser. Tipo, a FIAC quiser mandar 20, manda. Só que tem que ser o trâmite oficial.
Sim, passa por
A sua tese ganha. Pô, tá muito legal.
Não sei como que é o procedimento, mas eu acho que cada área tem um...
Claro, lógico. Nossa área vai para ciências agrárias. Quer dizer, a sua tese vai para ciências agrárias. Você vai pegar os especialistas da área. Eu acho que você tem chance muito grande. E você viu, o cara deu a dica, sei lá, do Zipozoc, né?
Eu
Não
tava na
perde.
conferência lá, eu conversei com todo mundo, né? Dando tiro. Sim.
Cara, o cara leu o seu trabalho. O cara viu o potencial, vai por mim. E você trouxe negócio de fractal, simulação avançada. Meu, do jeito que tá o nível do Brasil, cara, vai pra lá.
Não, com certeza.
Meu, entra de cabeça lá. O cara, eles têm esses negócios de bolsa, cara, lá deles. Às vezes tem um lugar na Alemanha, não sei como é na França, mas tem um lugar na Alemanha que a bolsa é vinculada ao professor. O cara tem direito a um pós-doc. Se for na França, for igual à Alemanha.
Professor, vamos voltar?
Vamos. Se me der a letra, depois eu traduzo você.
Não, tá.
Rangel, ready?
Vamos lá?
Jean-Yves, now it's going to be your turn, okay? Jean-Yves, can you hear? We can't hear you. No,
Your
microphone.
your microphone? We can't.
you need to turn on.
Turn on your microphone.
Turn
Eu não
on
escuto
your
a gente.
microphone. See the screen, it's off. Okay, take your time.
Ele tem que ligar lá nele. Vai chamar alguém?
Oh, okay.
Jean-Yves, ton micro est coupé.
Yes, how did you do? That's what. Okay. Yours. Okay, now yours is turned off. Both of you have turned it off. Okay.
Yes, I know.
All right. Okay.
Jean-Yves, ton micro est coupé. Il faut que tu le remettes. Ça marche pas?
Não, mas é o dele, não é?
Mas aí o cara não sabe onde tá o botão.
O Vincent está mostrando para ele, parece.
Eles são do mesmo departamento?
Não são universidades diferentes, o laboratório não aparece no mesmo.
Okay.
Okay.
Can you hear me now?
Yes.
Okay.
Okay. I just refresh the HTML page. Now it seems to work. Okay. Could you hear me well?
Yes.
Yes.
That's all right. Okay. So I like to thank also Luis and the supervisors for inviting me to this jury. I was really pleased to read your manuscript, which I find it very well written and interesting. And well, I've been working on DM since quite a long time now, and mostly at the beginning in the fields of mechanics and physics. And so now I'm very happy to see that there are new big studies in fields like teenage, which is it's obvious that it's really complex to simulate everything in this case. So you need to of course have some simplification, but that's great. That's people like you try to make models of this complex problem using these quite new tools like DM. So I have also many questions like Nelson. So perhaps you will not be able to say everything, but I can send you the questions. So if you want.
Yes, for sure.
And of course, Vincent took me also several of them because well, we have done our PhD in Montpellier together, so we are in fact very close, and we have perhaps the same way of thinking. Also, you will see that probably. So I'm going to try to be a bit. I don't know how you say that. To be make a step aside from what's has been said by Vincent and try to be more in the problems related to agriculture, but I don't know if I will be able to do that. So also my questions are not ordered, and so I apologize for that. Just one minor point about the text. I think it would have been very interesting for the reader to have a sort of a kind of glossary with all the notations and definitions, but of course not in the papers, but something, a sort of appendix with that. Perhaps it could have been more easy to read with this, but anyway, it's okay. There is no big problem. So my first question is on figure 5. So what was figure? Okay. Yes, okay. Well, it's related to that. Well, we discussed about the failure criterion of the aggregates, and I had a quite similar question as Vincent, and my question is why you don't use directly the p-value, as it seems that it seems that you when you on your stress strain curve, in fact you take this maximum value which is in position 3, and why don't you use directly this max value? Because the max value is there is no it's not well, it's easy to determine where is the max.
Because during the as you in this diagram I stopped before it happens, but after the aggregate ruptures the material rearrange, and then we start to increase the force, the compressive force again, and if you just choose the maximum force, it sometimes you may have the aggregate failure, but you are saving the data from different material that it was initially. So what I'm looking here is trying to get the first force that represents the aggregate failure, and then this arrangement of material may be a bit tricky if I just consider it as the maximum force.
Yeah, I understand. So you mean that you can have, for example, a first failure, a first crack, and after well, the material rearrange a bit, but you continue to push on it, so you increase again. And so my question was, is it possible to make something like that? Well, you push on your aggregate at the top, and after it will fall down. So
okay, yes.
You have not this this effect of breaking the pieces of the particles. It's not. It's just an idea like it, but I'm not sure it's a good idea. But as Vincent, I think it's always better to have a criterion which is a direct criterion. I mean, something that is absolute in a way. It's not. You don't need to have to choose some specific considerations such as the first 40% or something like that. It's
Yes.
well, it's your point of view. I mean, I know that in the field of in my field also, and in any field we use these types of criterion frequently. You can hear me?
Yes, yes, loud and clear.
Okay. And well, so figure 5 and 6. Okay. Well, well, it's the same comment perhaps as the sound, but you see that it's the curves are quite different, and my I well. I was wondering also if with this bond model, but you said that you can break in shearing, but I mean sometimes, well, if depending on the way you compute your force between the particles you bond, you can have a sort of plastic behavior. But I'm not sure. Of course, it's also related to this consideration about the model you use for gluing the particles. So, well, Vincent already said words about that. Well, I found the acoustic also very interesting, but I was a bit, well, not disappointed, but you are not using it. So it's really interesting to see that you can capture with the microphone where it will break, but you are not really using it. But it's just, I understand it can be done after, for example. And I was wondering, you see that the signal you have a strong peaks, but you have a lot of very small fluctuations, which can be due to a noise or a background noise. But perhaps it's also there is perhaps also information on perhaps mic cracks that can be captured or before the coalescence. So if you use two sensors, two microphones, one close to your particles and another one a bit farther, you can eliminate the noise which is coming from the room or other place, and try to have I need to simplify your these fluctuations and just and only just keep the fluctuations due to the crack close to the particle. So it's interesting to use two microphones. I don't know if you use two or not, but I've done tests like this with colleagues. And if you use two microphones, you can use one and for capturing the sound close to the aggregate, and another one to a bit further, to a bit far away, to eliminate all bad noises that are coming from outside.
Yes.
So, but it's just a suggestion. I don't know if you catch me.
Yes, I understood you. Actually, I saw a work from Evelyn Kolb. Recently, yeah. She used some sound evaluation to see the movement of earthworm in the soil. I think it's really nice. But what we have done here was only with one microphone and in a very simple way. And this background sound, I agree that it may is blurring the crack propagation, the small crack propagation, and because we have this background noise coming from the compressive machine. So where we turn on the engine of this machine, we have a natural background sound, and then this microphone was closer to the bottom plate, and then I think it in some way it is this background noise get amplified a bit more, and then but luckily I could identify this background by sound analysis in the software and remove this noise that I knew that was coming from this machine. But for sure, it could be a more precise way to try to identify even position of the cracks within the aggregate.
Yeah, I think it's interesting also for the field, perhaps, because you can perhaps put microphone in soil and test if you can identify this type of signal. But you can discuss with Mathieu Lamandé or Thomas Keller about that. But
Yes.
I think, well, there are plenty of experiments, and but I don't think they have used microphones, and that could be interesting, as we can eliminate, for example, the sound from the unwanted sound, for example, from the machinery.
Yeah.
Perhaps it's interesting to use it to see if you crack aggregates.
Yes. Yes.
To quantify how it's cracked. So I was also wondering, you see that you have shapes, and you don't speak too much about the shape of aggregates, but it has probably an effect. It's not spheres, and in your simulations you use really nice spherical shapes, but if you take this picture, still we see clearly that the aggregate is has a complex shape.
Yes.
And I don't know, but I used to make a model long time ago with my colleague Rajai, and we use, instead of the diameter of the particle, the height between the bottom and the upper plate, just at contact, and we had found nicer correlations than using directly an average radius of the aggregate. But I don't know which type of radius did you take for that? Did you measure the maximum size, or it's an average between different sizes?
Actually, I have used a common method that soil scientists use. That is the separation by the size of sieves. So basically, we performed the sieving process and separate aggregate by range of size. If you think that is not a very precise way, but we have a range within. We characterize the soil like a particle size distribution, and it gives a good idea about the size. But the numerical model is I think, in my opinion, the major approximation made by this model is this size and the geometry, because in the model we have more precise size, while in the soil we have a small range when we use sieves. So I would say that for this parameterization method, I think the shape effect is in some way we are considering to define the micro parameters of the model in order to reproduce the macro behavior. So shape is in some way considered by this aggregate parameterization method, because we have to define the parameters to reproduce the macro behavior. But I have worked with 3D imaging, scanning, to create that it's possible to scan the aggregate shape and recreate a mesh from this shape, and this shape can be used to be filled with spherical particles, and then at least the shape effect could be taken into account. And that is actually my next paper I'm going to work with, because during my time at Agroscope, I have worked with a collection of soil samples and have performed this scanning of the aggregate shape of a lot of aggregates. So I would like to do what I would like to do as a first paper would be to use these shapes, different shapes from different soil conditions, to use the same parameterization method and see if it improves the ability of the method to reproduce the macro behavior, and also to investigate the shape effect on the variable distribution, because I think the variable models can be very, very influenced by this shape of these aggregates. And since we have very defined shapes, like for compacted soil, we have a very sharp shapes, and for natural soil, we have more round aggregate shapes. So perhaps variable models is influenced by the aggregate shape, not only for the internal structure. So actually that is a paper I want to work in after all this is finished.
Okay. Um, um, so I jumped because I have several questions that have already been asked by guys. Uh, yeah, okay, so this one also. Yeah. Well, there is an analysis that we are frequently using, and but you didn't do it, but probably perhaps it can be helpful sometime. You didn't plot the probability density functions of forces. When you break the aggregates, you see that there are different forces into your aggregates, and there are zones that are really stressed and others that are not stressed at all. And of course, it's more stressed in the median plane, but it's interesting to see, depending on the porosity of the aggregate, how these forces are distributed, and it could be, you could easily plot the histogram of these forces for the different type of aggregates, and perhaps it can be helpful or can be interesting to discuss this distribution, as of course when you break the aggregate, somehow the largest forces are more important than the weakest one, and because they are close to the failure criterion. So if you plot these force distribution just by doing you just do a slide compression, you put you take all these force distribution into your aggregates, and you plot the histogram of the force, and you will see that probably that there are some forces that are more stressed than other one, and that are more important than the other one, and you can take these forces which are more which are greater than the other one, and localize where they are into your aggregate. So you can show where it will break and what is the most stressed zone, and if there are zones which are not stressed, for example. And especially for Pogo's aggregate, I think it would be interesting to see what happened. Does this zone of this very stressed zone is more localized or not on this aggregate? Well, it's just a suggestion.
If I understood correctly, you are talking about the polar histogram, right?
Yeah, because the Pogo's aggregate, and your aggregate, if I understand well, you have removed some particles inside to make porosity.
Yeah. Yes.
Yeah.
Yes.
And so they have different microstructures.
Yes.
And if you can by a simple compression before failure, you can have all the forces between the grains in all the bonds, in all the bonds in your aggregate.
Yes.
And you can plot the histogram of these forces, and it will be different depending on the fractal dimension you have. And you will see, for example, if for some aggregates you have a more broad distribution or more narrow distribution of these forces, and this indicates in a way it's a bit similar as the stress concentration, Griffith's stress concentration, but here you have not really failures. So you have flows, but you are not investigating the flows. But the information you have is how the bonds between the particles are stressed. And if you plot this distribution of how these bonds are stressed, what is the force into these bonds, you can normalize it by the average force, for example. You can see if the distribution of the force is more narrow for some aggregates than the other one. And that could help to understand how the stress is transmitted through the aggregate. But we can discuss that if you want after. And so it's interesting to see the variable lows. I find that they are nice. Well, variable low. There is no specific. Well, we say always everybody talk about this I don't know the word in English. This comment on dit maillon faible, Vincent?
Weakest link.
Yeah, yes, thank you. Weakest link. I have a personal translator. And so this weakest link, we always say that, well, this weakest link leads to variable low, but in fact, I don't think it's really clear. And in many problems, we found other distributions as different than variable low. But apparently here it's quite nice. Well, you have straight lines, and so it seems to work well. That's great.
Yes. In the review of the second paper made by Nag, we had a question actually about the use of this weakest link, but the reviewer was questioning me because the weakest link is for 1D. And,
yeah, it's working on 1D.
Yes, and I have considered this for 3D. And he asked me to comment about that. Well, I spent some weeks on that, but my answer to that was like when we use an isotropic material, like we have here, and viable modulus that is considered a constant for some materials, in this case, cannot be considered like a constant for when we have the change of aggregate size. This was shown by some empirical investigations like Perfect and K and Brownacki, also a classical investigation, because these guys saw that in 79 that when we use aggregates from different size, each aggregate size has a specific viable model. So is viable modulus a constant? It could be used to calculate, for instance, friability. In my opinion, there is a divergence between researches, because some researchers are just using the viable modulus from ceramic materials, for example, and considering viable modulus as a constant. But we have already data showing that it is not a constant. So viable modulus, sometimes used to calculate friability, in my opinion, is not a correct approach, because soil friability should be we should have one value of soil friability to measure and compare. Using in that way viable distribution, we would have one friability for each aggregate size, which is sometimes is not for me it not makes sense, because it's not a standard way to compare different soils and sometimes with different aggregate size, so a lot of friability in the same soil. So in this way, I searched for some investigations, even for material science, and guys proving that viable modulus is not a constant. And for that reason, I started to compare, or it getting interested in analyzing the correlation between viable modulus and the structure of the aggregate. Of course, we have the effect of shape, but I have done some works in here, paper number 1, trying to get a relationship between viable modulus and crack size distribution. But I have another paper that is not in this thesis, where I'm working with Thomas to show a relationship between viable modulus and this crack size distribution. And also we found a correlation between viable modulus and the number of branches, and viable modulus and the number of junctions. A strong correlation between these structural features. So the question, answer the question, how did you consider the 1D to using 3D? Actually, I am using viable modulus, but some explanations from these aggregate features, structural features, is affecting the viable modulus or viable distribution in a different way. I try to get some ideas from these different papers and put everything together to explain to the reviewer that is not a concept, a closed concept, that we have a full understanding about it. It is still coming up some new discoveries, some new findings about this viable distribution. But I think it is a really inspiring field to work.
Yeah, yes. And yeah, for the figure 8, for example, yes, you just talk about that. You correlate. You hear me well or not?
Yes.
I have sort of okay. Yeah, it's interesting to see that you manage to find a link between the variable modulus and the crack size distribution. And but I was well. I worked on a problem which was a bit similar in a way, but in my case, we had flows, sort of 2D cracks into the system, and but with tomography it was not possible to see them because they are like micro failure, very close failure, and it's interesting to see that. Well, your graph here is based on the result of tomography, yeah?
Yes, yes.
And you manage to really see when you have this pore structure, and this pore structure apparently is the good information to have the link with the variable modulus. But you could have also 2D flows into your system or things that was not visible using tomography. So, but apparently it seems to work well.
Yes, this tomography, we had a resolution of 90 micrometers. So everything below 90 micrometers, like a surface flow, as you said, perhaps we couldn't incorporate in this crack size distribution. But volumetric flows, like larger pores, were considered for sure larger than 9 micrometers. And as I told you, crack size distribution in the way we measured is with the medial line. So we didn't measure the effect of the volume of the crack on the variable module. We just considered the crack size distribution as the length of this medial line of the pore, and plotted the distribution and found this exponent of the power law distribution. This exponent is actually the crack size distributions we are using here. And it was nice to see from the figure 4. No, sorry, from the figure 3, that we have two regions with different crack size distributions, S1 and S2 and S3. For this plot, I have used the correlation between the crack size distribution in S1, because using this crack distribution, I reached this relationship. However, if you consider the distribution in S2 or S3, this correlation is not, it didn't work. In my opinion, is that the structure of the aggregate near S1 is supporting the load. After we have this rupture of the structure near S1, the inner structure of the aggregate doesn't affect the tensile strength of the aggregate in the same way that S1 affects. In my opinion, S1 supports more load than the inner part of the aggregate, and it ruptures. Yeah, it controls the variable modules.
Okay. Okay. Yeah, well, so for the second paper, page 37. So well, we discussed about that, but the way you make your aggregate is to put all the particles which are monodispersed into a sphere, and after you glue everything, then you remove some grains. Well, it's just a comment. It's I don't know if there are other ways to do that, but it's not really well, it's not really physical, you know. It's like because you remove particles to your aggregates that you could have also you could have made, for example, your aggregates by adding cohesion between particles and trying to make them in a more natural way. But I understand. I mean, these aggregates are you made. They have a very specific microstructure, I think, which is due to the way you make them. But there are a lot of people who have investigated the way to make structures like this with big pores into it and using TM, and it's not really easy, in fact. I understand well why you have done that, because it's difficult to make not dense structures with TM. The particles tends to compact, and making large and aggregate with a pore structure, it's a bit difficult. But we can think about something else. For example, doing particles coming from I don't know, put an attracting point, that you have particles that are going to which are attracted to the points, and when they touch, they glue together so that you can control the way to have different types of aggregate with different types of microstructures. It could be interesting, but I mean, this way you have used is interesting, but it's not the only one. You can do aggregates in other ways.
Yes, I knew that, and the parameterization method, I think can be used for different aggregate formation methods, because you can choose the way you want to create your aggregate. I choose a simple method, but the parameterization method is pretty much the same. I think that's a nice point.
Yes. I think it doesn't work. There is no problem with your method, with your the parameterization method, and also you are not really interested in how at really local scale the microstructures drive the failure or something like that. So it's not so important, I think. But anyway, that's, I mean, it could have been, it's another thesis probably, but you could, somebody could try to see if with another types of aggregates, I mean, there is a large field of investigation on that, on how this aggregate fails and how the microstructure of the aggregate play a role in the failure, and depending on how they are created. But it's perhaps more a problem of physics than a problem of soil science. So yes, for the coordination, I think it's related to what I've just said. It would be very interesting to see to have the coordination number of the bonds, of the group bonds, and for example, for a grain, it's glued to other grains. You can count the number of group points and divide by calculate the average of these group points. But you have also the possibility to have contacts. So you can also make a coordination number that account for the contacts also. You can make, for example, two coordination numbers, one with only the average number of group points, and one with the average number of group points and contacts. And it's interesting because you can activate some contacts without having good points. So to investigate the microstructure, I think it could be interesting. Well, you tell me if because I don't take I don't took the time at the beginning, so I think I'm perhaps running out. You are running out of time, so you just tell me when you want me to stop.
Okay, feel free.
And
Take your time.
Continue.
No, I understand that I'm free, but I mean I just want to.
Yeah.
You just.
We are about 35 minutes.
Okay.
Okay.
Okay. Yeah, I just two minor points, and I finish with that. For the dissipation of energy, I don't like viscous damping at all, but anyway, it's not, well, it's okay, but the viscous damping is a bit dangerous because it's a global viscous damping. If it was a local one, you can consider it a bit like a way to dissipate the energy at the level of contact. In a way, it's related to the I don't remember the word for that, but when you the restitution of energy when you collide two particles, you have a loss of energy, of course, when you have a collision between two particles, and if you take it into account at the local scale, it's okay because there is something physical with that. But if you take a global viscous damping, it's like told it's like having the particles into a fluid, and you have all these particles are subjected to drag forces, and well, this has a really strong effect sometimes on the way you dissipate energy. It dissipates energy very rapidly, and so well, it's okay, but it's interesting to see, for example, if you run a simulation, you can evaluate very easily what is the influence of this force, and you can, for example, output it from Yev and see if this drag force on particles is, for example, greater than contact force or greater than, I don't know, friction force or something like that. Just to see, to evaluate if these forces, these drag forces, are of the order of magnitude of other important forces into your system, or if they are just negligible and they are just here to dissipate energy. So it's you can check if you want, but
Yes.
And for future works, it's interesting. I think for you to do, you can do a test, for example, a compression test with this global viscous damping and with the other one, and you can see that you will see that the global viscous damping is really it affects a lot of the simulation if you increase the velocity. So it affects the dynamics of the problem a lot.
Yes, yes.
So, but you can do tests for that,
Yes,
but it's okay. There is no problem. You can do that for
I
if you have time.
I have a question actually here about the computational time or computational effort when we use the local or the global. I've made some tests with the global and the different contact laws with the local, and I saw that when using global, it seems that the computational time reduces significantly, and yeah, that was a strong point to choose the global instead of. I know the troubles of the global, and I also agree with you. We have to be aware of this. But for these kind of simulations where we have a lot of particles not yet the real number, but we have still a lot of particles. So I try to optimize the code, and global seems to help a lot in this.
Yeah, I understand. Yeah, we always have problems like this, of course, but it depends on what you want to tell with your simulation. So, but anyway, a simple way to discuss this is to evaluate if this global viscous damping has a very strong effect on the particles. When, for example, you take an aggregate and you move it at the velocity of your of your tool, and you can evaluate which drag force is exerted on it.
Yeah.
And if it's negligible, there is no problem. But I understand there are plenty of strange things that we use in DM to try to optimize the parameters, because the computational effort is sometimes very strong. And yes. And yeah, well, my last point, and I will send you the other one if you want. But my last point is that you validate your model of aggregates, and that's good to do that. But I think it could have been very interesting also to validate it also on a larger scale. For example, by doing a odometric test or something like that with several aggregates. It was not so complicated for you to have everything. So you could do a consolidation curve or something like that, and check whether it gives or not a good stress strain curve in the consolidation, or well, you could do also a three-axial test, but the three-axial test is a bit complicated, or because you need to have a sort of membrane. So but that could be interesting. You can see also, you can evaluate how many particles are wrecked during this compression test, and that could make also a paper, I think. So thank you very much for this thesis, and for your presentation, which was very nice. And sorry, because I was a bit long, so and I will send you the other comments.
All right.
Okay, thank you.
Thank you very much. We certainly will give a bit of thinking on your comments, and certainly will introduce some in the final version of the thesis. Thank you very much again. Now I will invite Dr. Garcia for his comments.
Okay.
Please.
Thank you so much, Carlos. Thank you, Luis, for the invitation. I'm not soil mechanics specialist, and
Just let me Can you hear him? Okay.
Not very well.
Not too well.
Maybe you have
Microphone is in the camera.
I think it's just your orientation when you speak.
Okay. Better? Better now?
Yeah, much better.
Okay. And I'm not specialist in soil mechanics, and I'm learning. And don't scare with my basic questions. And I try many questions I wrote, and I will send you to discuss with Antonio Carlos if pertinent or not. But it's a different point of view.
Yes.
Because I working with control systems and machinery. I'm not a specialist. And well, my first question is about the return the discussion of the geometry, the shape of the aggregates. Yes. The shape influences the force, the resistance, the force, the damping. How does it work?
Actually, yes, for sure, but I didn't isolate this variable.
Okay.
So, for instance, when we have sharp angles, like in a compacted soil,
Okay.
we can have more like a pyramidal
Okay.
format. And in my opinion, I didn't. I performed library measurements, but that region in S1 may suffer more when we have a smaller area in that contact point. So the distribution of the force within the aggregate structure is not homogeneous. So we have different force chains in the structure of the aggregate, and it affects for sure in the distribution of the force, and consequently this perhaps in this damping effect, because of this crack distributions, the speed of this crack distribution may also affect this wave propagation of stress within the aggregate structure, but it was not investigated in here.
Yes, because looking at the figure 1, the shape of the aggregate in figure N is a pyramidal shape.
Yep.
And in your simulation figure
Spherical.
2, spherical.
Yes. Well, as I told to Jean, I think this is a major approximation of the model, and I try. The parametrization method in some way considers this shape effect.
Okay.
Because we have to define, we have a macro value from the lab measurement, and we have to choose some, or to define the micro parameters of the model to reproduce that.
Okay.
So in certain level, it takes into account this shape effect and other stuff that we are not looking.
And the shape of the, I don't know, the micro particles.
Particles, you can say.
Particles, yes,
Yeah.
yes. You are in your model is a spherical.
Yes. It saves a lot of computational time.
Is the same spherical size?
Yes, it is monodispersed.
Yes.
The same size, the same stiffness, the same density.
In the real soil.
It's totally different. You can have as much particle materials
in
as
the
possible.
in the program, can you put program the randomly diameters?
Yes, you can have.
You try this? Or?
No, I didn't went to this. I didn't go to this direction. But my random.
In your opinion, is bad or not influence the results?
I think when you look at the bulk soil and the macro behavior,
Okay.
these more detailed particles, material and shape, it increases the computational effort.
Okay.
I mean, if you look in micro scale, it is better because you can increase the details about the mechanisms involved in the fragmentation process.
Okay.
But when you look at the macro scale, saving computational effort is important.
Okay.
So if you can simulate the same micro behavior with a simple model, it's better because you can model larger number of particles.
Yes. That's because how far you stay in atomic ligations, for example, CFC or CCC, crystalline structures, and the computational force is huge, very, very huge.
Yes.
And how far this model is from the atomic models?
I would say that in terms of scale, it's I don't know, 10 to 9 But in terms of similarity, I think it's pretty much the same
Okay. Okay, nice.
or very similar. Because actually discrete elements has also the name of molecular dynamics.
Mhm.
Yes, because you can use this to model, for instance, the behavior of fluids.
Yeah.
Yes, but in a smaller scale.
Okay.
That's a tricky question, actually.
Yeah.
I've never thought this.
Okay. Oh, another curiosity. Why the displacement, the velocity of compression is different in the real world and in simulation?
Yes.
Why?
Vincent has asked you about this, yes, because when you try to reproduce the same speed compression rate, the computational time increases a lot. So
Okay.
I performed 900 simulations. It took me like 2.5 months to perform
Okay.
everything. With this, it's different speeds. If I use the same speed from this experiments, it would require more time.
You tried once?
Yes, I tried to perform a
check
comparison. Yeah, yes.
the results?
Yes,
The same results?
It's a bit different in terms of the variation of the force with the displacement.
Okay.
Because when you reduce the speed, this wave effect of stress reduces.
Okay.
And this quasi-static compression test becomes more realistic.
Okay.
But in terms of macro response, this higher speed can get the very, very, very similar macro response.
Oh, nice.
But with this difference in time computation.
Oh, yeah. And what another question is in the figure 8, page 29. You use 3 points.
Yes.
3 points. Is 3 points sufficient to this kind of analysis? To take some the linear equation with.
Yes, at least I would say that at least 5 would be better.
It would be
Yeah,
better.
but these 3 points, it's because we performed the X-ray microtomography for 3 aggregate size.
Okay.
And just to you have an idea, one tomography for one aggregate with using this configuration of 9 micrometers took around 4 hours. So it is a very expensive method. It's still very expensive method. And then we have to reduce this number of analyses. And I try to be careful writing this paper, telling the reader that this is an exploratory work and should be evaluated in a larger sample.
Perfect. Perfect. And another question is. Oh yes, paper 3. In the paper 3, the you don't use the universal soil equation to to model the utility forces. Use just a Azai or Azabi equations, but Azabi equations has a very, very large error in the force, predictive force.
Yes.
And but you use no problem.
Actually, the Azabi and Azai were used to fuel consumption estimation.
Only for the
Only.
draft force?
Draft force were numerical data.
Numerical data.
Yes. I agree that Azabi has some approximations, and but to compare the current when you do comparison, I think it gives us a good idea of the larger number, just to see if it increases or if it decreases. I think it's okay to do this kind of analysis.
Because using the universal soil movement, the main parameters is I don't know, is the soil friction angle equation, and but you don't use this.
I didn't
parameter.
touch because this universal equation, if I can remember the name. Yes, yes, it's very very complicated. But this universal equation is based on mainly on continuum medium. Yes, and it didn't consider the effect of the mechanical behavior of the aggregate into the macro behavior of the soil. And since it happens, I thought that it didn't make sense to compare both, because one is an analytical approximation used. I think for in civil engineering it helps quite a lot because it's near to a continuum. But for agricultural soil, where we have a larger pore sometimes than the aggregate, it makes no sense. And then we have the numerical data, in my opinion, that can be more realistic.
Realistic, okay. And in the paper 3, can you explain something about the RFO
principle?
Yes. Why do you
came with this idea?
Yes.
Yeah.
Yes.
Okay.
Basically.
Mainly, the goal of the paper number 3, despite I'm comparing both tools and showing that one is better, that was not the real goal. Our goal here was to apply the parameterization method and show it can be used. It seems that it can be used in a practical way. But I have worked in a laboratory here, in CTV, and there we have worked with some tillage to reduce the impact on soil structure.
Okay.
Basically, is reducing the size of the area of disturbed soil.
Okay.
And this idea of this tillage tool came during that work. So I don't know. Actually, I don't agree that RFO should be used, it should be implemented, because we have another kind of problems that we solve in simulations actually. Ejecting a lot of particles into the air, creating dust and stuff like that, reducing the aggregate size sometimes to dust.
Okay.
I think that's not the way to go. But what was important in choosing this tool is that the principle is very different from the conventional one. So if my model can see this different, I think it was a nice example to see if the model could identify differences between these very different tools.
Okay. Okay. And because the new implement, you have a rotatory machine and a torque, and the section area is smaller than the conventional implement. And sugarcane development is a problem or not?
Actually, this was thought to allow, I don't know if the guys in French knows, but here in Brazil we have the sugarcane planting, that the distance between the rows are conventionally used 1.5 meters. But in this laboratory we found that planting with 0.75 meters would increase the productivity. So, but using the conventional tool is too large, the area of soil disturbance. And when you promote this furrow opening, in so small distance, one work affects the other.
Okay.
So we had to develop a new tool, narrow, to promote the furrow opener and structuring the furrow
Okay.
in a way that didn't affect the other row.
Okay. Nice.
That was the idea.
Okay. And this the furrow opener and the rotational furrow opener are operating in the same velocity,
2 meters per second.
2 meters per second.
Yes.
Because in the table 5, in the
Consumption.
power demand and diesel consumption,
Yes.
line diesel consumption
Yeah.
liters per hour, 16.4, and liters per hectare, 16 per 0.4, and 1 hour you prepare
1 hectare.
one hectare,
Yes.
and our fuel you consumption 13.8, and consumption per hectare is 9.2.
Yes.
It's
Actually,
not at 13.8
actually, the speed.
for the same speed.
Yes, actually, this data from the FO row, FO column,
Okay.
are from the empirical data. So what Brazilian producers are doing. So the number is 1 hectare per 1 hour per hectare. Yes. But with these tillage tools, RFO, we estimated that it increases a little bit the yielding of the tool. I
Increase
wrote
the
this.
velocity.
This is because the increment of the velocity and the operational time in terms of maneuvering and refueling, stuff like that, we considered a higher yield of this tool
Okay.
for this calculation. It's here in page 71. The resulting operational yield is of 1.5 hectares per hour for this tillage tool.
Why?
Because it increases the operational speed. From nowadays it is like 3 to 5 kilometers per hour. And when you use the RFO, the development was for 7 kilometers per hour, and giving us
They have a
operation.
different velocity operation.
Sorry.
They have a different velocity.
Yes, yes, in the operational way. But for our model, we consider the same speed.
Ah, okay, okay, 2 parts.
Yeah.
Ah, yes, I confused. And I like the figure 9. I like a lot. To take a power used PTO, how do you estimate this?
This is these are equations from this ASI 83.
83.
Yes, you can estimate the draft force.
Draft force
Yes.
is different PTO.
Yes, using there is a correlation.
Because the efficiency is
Actually,
different.
these are based on empirical experiments in, I don't know, in some laboratory in USA. They performed a lot of experiments to create this standard way to correlate draft force, PTO, and engine power and stuff like that. So
Yes.
ASI has an approximation to calculate this.
Yeah. And because in Azabi, you need some properties of soil properties with another. I don't remember.
I'm picturing the figure. you know that we have the coefficients to get the PTO or engine power, and for this you can choose between sandy soil or cohesive soil, or if you are running in a concrete.
Yes, yes. And you don't put these considerations in your
Yes,
tests.
yes, that's true. That's a good point. But I assumed that
Yes,
I was talking
because
about
the velocity is
yeah.
an important parameter
Yes.
for this equation.
Yes.
If you change the velocity, you need to change the draft force.
Yes, yes. Yes.
You came back to the equation and put another velocity and recalculate the draft force. Okay. I try to find here the ZAB, but okay. You need number of tools, soil parameters, and velocity, and and the deep tillage deep. And if you change some parameter, you recalculate everything.
Yes, but you are talking about the calculation of draft force.
Draft force.
Yes.
What draft force you use to calculate the power.
Yes, exactly. But in table 5, there is another. I think in the same document of Hazai, that you have a different picture correlating some parameters like 0.92, 0.83 to obtain the drawbar force, and correlating with PTO, correlating with motor engine. Yes, that was I have used.
Yes.
Yes,
Okay.
yeah.
Yes.
And the draft force, I just considered the data from numerical simulation.
Yes, nice. And to finish, another question is, in general, the main conclusion you put in the last phrase or last part, and I inverted. I put them in the first. For example, in the article 3, your last paragraph is, as a result, using the new tool concept in Brazilian sugarcane production, we estimate a fuel consumption economy of 44% compared is the first conclusion, is the most important conclusion.
Yes, I put in the end because
Yes.
I think since we wanted to apply the model and show that it works, and the resource that it could provide to tool design.
Okay.
In my opinion, the fuel consumption it's interesting to see that we can obtain that, but it is not the main focus.
But it's sell your art, your paper.
Yes, no,
For
I agree.
everyone.
I agree, but with a certain caution, because this is just a scratch on the.
You put you explain it's a simulation.
Yes.
Be careful. Okay, nice. But in simulation, we obtain estimated fuel reduction economy 44%.
Yeah.
Okay. Be careful. Simulation. Okay, nice. And I take some another question, but it's my main questions. And again, thank you so much for the invitation, and congratulations for your job in US, for your job. I like so much.
Thank you. Thank you, Angel. Thank you all again for time and patience. At this point, I will invite the audience to leave, please. And we're going to have a discussion, including you, Luis, to leave for a while.
Okay.
And we have a discussion. Don't go too far away.
Yes.
Unanimous decision, your approval unconditionally. Okay? So congratulations. And let me be the first one to call you Dr. Barbosa. Okay? Then you have your time for your comments.
Well, it was a very challenging period. However, I'm lucky because the love of my life, my parents and my friends supports me. But I imagine the ones who feel alone in this darkness. With this in mind, I realized the numbers showing the depression among postgraduate students has dramatically increased. It is our duty as active scientists in society to identify the cause and treat this disease. A contribution to overcome this, for instance, is the honest and inspiring guidance similarly to the one I have had. For this, I would like to congratulate Professor Dr. Antonio Carlos de Oliveira Ferraz on behalf of all masters and doctors who had the privilege of working with you. For this, I have this small gift.
Oh, thank you. Thank you very much.
All the postgraduate students and professors.
Terrific.
It's a frame. It's a frame that we have all the words used in the dissertations and thesis oriented by the professor, and it's a cloud plot where the larger is the word, the most it was used in your work.
Okay.
And it is
What a
signed by
surprise.
everyone.
Thank you very much. Very precious. Thank you.
Thank you.
Okay. Oh, he's the guy, not me. But in closing, I have to explain the tie and the jacket. Okay. He is my last student, and that's the reason this section is so important to me. And I would like to thank you first, Luis, for letting us finish, my last work in my career, at least of this kind, in such a brilliant way. Thank you very much. It was a real pleasure working with you and following your progress and achievements. And thank you for being such an important member of our team. My wishes for you is for the best in your personal life and in your career as well. Thank you very much. Okay, with this, I formally close this section, and I thank you all again. Thank you very much.
Thank you.
Thank you.
Thank you.
I wish you will enjoy.
Professor Vicente, Professor Yves,
Yes,
I would like to say that Luis is an excellent candidate for a postdoctorate in France.
I know. We only need funds.
All right. Thank you very much for the invitation.
You're welcome.
Bye-bye.
Thank you.
Okay,
Bye.
see you guys.
Thank you. Bye.
Thanks.
Okay.
Obrigado. Surpresa, Luiz.
Arthur, eu assinei.